Good afternoon. Welcome to a riveting Memorial Day weekend where we will be discussing combined spectral problems, specifically problem J. I don't know what better thing we could do on Memorial Day weekend than do organic chemistry, so very excited. I'm Amanda and I am taking the spring, well, technically summer semester of organic chemistry 1 with the University of New England. So we have a plethora of spectra here, and we're going to determine what the potential molecule is. So the first thing I did was calculate degrees of unsaturation. Through my calculation, I found that there are 5 degrees of unsaturation. So right here, I start to think if there's a double bond ring, that would be 3 plus 1, so that would give us 4. And if we're missing one more degree of saturation, my guess is that it's probably a carbonyl group of some sort. So IR spectroscopy measures the absorption of energy into a specific bond. Each type of bond will absorb a different energy, and this is really what determines our functional groups. So if we start here, we could probably get an idea of what we have. So specifically, the first thing I see is a carbonyl, a double bond between a carbon and an oxygen. So that's this guy right here at 1700. And the next thing I notice is you've got some sp3CH stretching and sp2CH stretching. So that's these guys right here, sp2, sp3. So you got one at 3000, the 3000 guy, well, the 3100 stretch is sp2CH, and the 2900 is the sp3CH stretching. Other things I looked at to determine what this molecule was is immediately I saw the double bond carbon-carbon stretching, which I assume is from the aromatic ring. So we see that at 15 and 1600. So you got these guys here, 1500, 1600. So here is where I thought there's a bunch of peaks here. You know, this is the aromatic ring region. So maybe we're on track with that theory. Other things I'd noticed, there is a single carbon-carbon bond, sp3, at about 1150-esque, maybe 12, now that I'm, wait, nope, but 1150 I'd say. So we're going to highlight this guy. So to summarize, we potentially have maybe a ketone, maybe an aldehyde, and I'm assuming a benzene ring. You know, I don't see that aldehydic hydrogen stretch in this region, so probably a ketone is my assumption. Moving on, if it allows me to move on. Maybe not. Here we go. So now you have the IR table. And the IR table is basically a summary of what we've discussed. We've got the carbon double bond oxygen bond at 1700. We've got our CH stretches, sp3, sp2, 3100, 29. We've got the aromatic ring stretches, and then you've got the single carbon-carbon bond stretch. Moving on to 13C spectroscopy. 13C spectroscopy involves molecules absorbing electromagnetic energy in the radio frequency range. So here we find a number of unique carbons, the number of unique carbons, and the chemical shift, which the peaks tell us the chemical environment of the carbon atom. So we're going to go back into draw here. So this is where I was more confident that we have a benzene ring, because in the benzene ring region, we've got all of these guys here between 120 and 140. So I'm like, okay, we probably have a benzene ring. To get specific, I think the aromatic ring carbon double carbon bond here is the carbon that attaches the substituent to the benzene ring. So it's the carbon that literally connects the substituent and the benzene ring. And my assumption for this is because this carbon is more de-shielded because of the aromatic ring, and it's also part of that large substituent, which is including a carbonyl. That double bond and oxygen creates pole. The benzene ring creates pole. So I assume this peak is more out to the left given that position of the carbon. There are basically two sets of adjacent carbons on that benzene ring, and I think that this 129 are the four carbons, that tall peak, and then you've got one last one that's kind of hard to differentiate, that's a bit shorter on this side. So this peak, this short one, more towards the right, is the furthest carbon from the ring, furthest carbon from the substituent. So if, like, let's say we go, here, I'm going to go forward to my proposed molecule and show you. So if we're looking at the proposed molecule, this is our guy at 142. These are our parallel carbons that I believe this peak at 129 represents these guys. And then your peak that's furthest to the right at 127 is this carbon, which is furthest from the substituent. And my thought process is that because this is furthest from the carbonyl oxygen, that it's not pulled as far to the left. So that's why I think this guy's 127, these are 129, and this is 142. So going backwards, we'll continue. You've got a peak all the way out here, about 210, which is your carbon double bond oxygen bond. So that tells me we probably have a ketone. So now I'm feeling confident we have a ketone. And I'm going to highlight for that for you about here. And then you've got two more peaks here, which I know that's carbon-hydrogen bonding. And I believe the 45 is the CH2 carbons on the substituent. So I think that there's a methyl group at the end of the substituent all the way to the right, and then there's two CH2s, and then you've got your benzene ring. So I think the 45 peak is my two sets of CH2s because the carbons there are more de-shielded because they're between the benzene ring and the double bonded oxygen. So they're being pulled in both directions. So I think that creates this basically signal that's more left. So that's why I picked 45 for these carbons specifically. And finally, my assumption at 30 is that we have the methyl group that's alone on the right side of the carbonyl. So toggling back out to show you on the proposed molecule, think this is our 30 and these are our 45s. And again, this is a hunch. So moving forward, this is the table with all of the things we discussed. Now finally, we're at 1H. 1H gives us information about different types of protons, ratio of protons per resonance, multiplicity, and chemical shifts, which are basically bonding environments. So thus far, we've used up all of our degrees of saturation. We know there's an oxygen that's double bonded to a carbon. So we know there's a carbonyl. I'm pretty certain it's a ketone, and that this is suggestive of a ketone based off of what I'm seeing. We know there's a methyl group on that ketone. We think this is a monosubstituted benzene ring because out of the 6 carbons, 5 of those carbons have hydrogens in the aromatic ring. And we can see that. So we see at 7.2 ppm, 5 hydrogens, that's our benzene ring. And this is the benzene ring portion of the spectra. Then we now have to contend with what's our methyl group and what's our 2 CH2 group. And this is where I kind of got stuck. But again, this is a spectra, and there's theory and then there's reality. So my thought process is there are 3 hydrogens, there's a singlet, it's a tall, intense peak, which tells me that these hydrogens are on a carbon, and that carbon has a neighbor with no carbons on it. So these hydrogens have no neighboring hydrogens. So that establishes for me that there's a methyl group and that the carbonyl group is is at basically the end of that substituent, you've got following two CH2s, and then you've got your benzene ring. So because of this tall, intense singlet, and then you've got this multiple peaked, less intense section of the spectra, that's four hydrogens. It leads me to believe that they're indeed on that substituent two CH2s followed by the methyl group. I've played with this molecule multiple times, and there's no other way I think that this molecule could most likely look. I didn't see doublet of doublets, so this is my best guess. So moving forward, this is the table in which we summarize our findings. And finally, this is the proposed molecule and molecular formula. So like I said, we have a benzene ring. We have a carbon attaching the substituent. And the benzene ring, you've got two CH2s, and you've got your ketone and your methyl group. And with that, I thank you so much for your mentorship, and thank all of our teachers for all of their hard work. Have a great day, and thank you so much for this semester.